Hi, this is Inyoung, and I'm a PhD student in Seoul National University, and I'm here to introduce the paper titled T-Rust, a compilation framework for in-process isolation to protect safe Rust against untrusted code. This is a joint work with Seoul National University and UNIST. Rust was invented to help developers build highly safe systems. It is increasingly popular in industry as seen with its adoption by significant players like NPM, Cloudflare, Amazon AWS, and Dropbox. Rust has been even merged into the mainline Linux in October 2022. The language is primarily focusing on memory safety, which is achieved mostly by compile time checks. Notably, Rust is known to be faster than security-optimized C/C++ and is targeted at replacing C/C++ and possibly Python, Java in some aspects. So let's take a look at how memory safety is enforced in Rust briefly. In Rust, thanks to its ownership model, it is not allowed to have both variable temp and buffer in the first example, pointing to the same heap object at the same time. This policy helps the compiler catch violations of memory safety easily. Additionally, it guarantees memory safety by performing compile and runtime checks, such as type checks or bound checks. Even in the seemingly flawless Rust, there are unchecked codes that can threaten memory safety. First one is unsafe block, and it is used when breakage of some Rust memory policies is inevitable for the sake of expressiveness and performance. This includes practices like pointer arithmetic on row pointer address and direct manipulation of metadata of Rust data structure. The second one is external libraries written in foreign language, as Rust can be mixed with libraries written in other languages. For example, if you want to call libc function in Rust program or write assembly codes for low-level programming, these are scenarios that fall under this category. For this case, you cannot assume that source code is always available since it can be served in a form of binary executables. Normally in Rust, overflow is prevented due to compile time and runtime bound checks. However, in the first example, there is a row pointer address access on the array, and the pointer arithmetic is performed on it. These instructions are considered unsafe, and through this unsafe code, an overflow is occurring beyond the original size of 5, bypassing Rust memories policy. The following example in the paper Cross-Language Attacks illustrates how code written in a foreign function can pose significant risks on Rust program. In the Rust code on the left, there's function pointer fptr, and the subsequent line calls a vulnerable function written in C. In the C code on the right, due to an overflow, Rust's function pointer fptr gets overwritten, and thus it leads to the arbitrary code execution. To sum up, Rust program is composed of two distinct pieces of code, safe blocks and unchecked code with potential exploits. Even though safe Rust is protected by Rust memory policies, vulnerabilities in unchecked code can undermine protection in safe Rust. So it is natural to solve this issue by in-process isolation. Various in-process isolation mechanisms have been developed as indicated in the provided table. For instance, Xrust requires developer to manually mark unsafe heap objects and isolate them using SFI. But it doesn't offer protection on stack and isolation from external libraries. Sandcrust uses expensive inter-process communication to quarantine external libraries only, and it doesn't handle unsafe Rust. Likewise, Fidelius Charm protects safe Rust against foreign libraries, but it relies on kernel modifications to switch privilege levels. The noteworthy point here is that no technique has been fully automated, including concurrent work, which is pkrusafe, that uses dynamic profiling to isolate heap objects from user annotated external libraries. Furthermore, there's still no method that ensures the protection of safe Rust from both unsafe Rust and external libraries. So in this context, the goal of T-Rust is to develop a mechanism that protects safe Rust objects from both unsafe code and external libraries in a fully automated way. Here, safe Rust objects refers to memory objects that are not touched by untrusted codes. The figure depicts the goal of T-Rust. Only safe Rust can access safe Rust objects, while accesses from unsafe Rust and foreign language are denied. But there are challenges to achieve this goal. First of all, unlike the unsafe block, external libraries cannot be isolated with SFI. It's because external libraries can be delivered in the form of executable binaries. IPC or kernel intervention, which were used by previous techniques, are so expensive to use. So in this case, Intel MPK will be the perfect fit for this purpose. So T-Rust automatically instrument entry and exit gate before and after calling external functions. Secondly, automatic identification of unsafe objects and their allocation sites is difficult for Rust programs. It's because Rust's encapsulation on heap allocation hinders identification of allocation sites. And it causes traditional context-insensitive analysis to conclude all pointers share a few allocation sites. Without precise distinction of allocation sites, it's impossible to determine the flow of memory objects, making automated analysis unfeasible. So here's the overview of T-Rust. T-Rust uses context-sensitive static analysis to identify unsafe objects touched by untrusted code in fully automated way. T-Rust then classifies an allocation site unsafe if it finds a flow from the site to a memory access instruction in untrusted code. T-Rust, as the below diagram, applies SFI to isolate safe Rust from unsafe code and applies MPK to safe Rust to isolate from external libraries. To distinguish unsafe instructions and external codes, T-Rust first modifies Rust compiler to collect unsafety information and external library invocations. In the first step, T-Rust mark all instructions used in unsafe blocks as unsafe code and mark all calls to foreign function as external library call. In the next step, to identify unsafe pointers and allocation sites, T-Rust collects pointer information to find all pointers used in unsafe instructions, and such pointers become unsafe pointers. And then T-Rust performs points to analysis and value flow analysis to identify the allocation size of unsafe pointers and track its uses. But due to the aforementioned challenge, T-Rust requires function cloning to improve precision. Based on value flow graph, T-Rust finds all meaningful call sites contribute to allocation and clone the corresponding callee functions. And then call sites are replaced with call to clone functions, and function cloning by this way contributes to improved analysis precision by distinguishing allocation sites and enabling context-sensitive identification of unsafe flows. So, as a result, how programs are transformed by T-Rust? Let me explain you by example. Here's an original Rust program. As I said, T-Rust first automatically identify unsafe objects that are touched by unsafe Rust. In the example code, PTR is being used in unsafe code, so T-Rust classifies it as an unsafe object. And then T-Rust automatically identifies allocation sites of unsafe objects. Following the flow of unsafe object PTR leads to buff, so the first allocation site becomes unsafe. And then T-Rust instrument codes to quarantine untrusted code using MPK and SFI. In this example, C-written function is called, so gates are instrumented before and after, and SFI is also applied to PTR in unsafe block. So we implemented T-Rust in two versions. First one is T-Rust using jmalloc as an unsafe allocator, and second one is using memalloc as an unsafe allocator. And all the safe allocators are ptmalloc as it is the default allocator of Rust. We measured normalized execution time with the 11 widely used Rust crates and compared it with XRust. So as a result, T-Rust shows 9% overhead with JMalloc and 7% with memalloc, while X-Rust induces 26% overhead. Although only T-Rust protects safe objects on the stack and quarantines external libraries, thanks to address masking and selective SFI using unsafety and foreign function called metadata, T-Rust outperforms the X-Rust in performance. We measured memory usage on 11 widely used Rust crates and compared it with X-Rust also. And the result came up as T-Rust with JMalloc shows 35% overhead and 13% with memalloc as unsafe allocator, and while X-Rust inducing 7% overhead. We deem this result is due to allocator characteristics, where bin-based allocators such as JMalloc is known for its initialization overhead of size-segregated bins. In conclusion, Rust is gaining reputation for its memory safety while maintaining efficiency. Unfortunately, unsafe code and external libraries in Rust may undermine whole program's security. To tackle this issue, T-Rust is the first attempt to automatically protect safe Rust from unsafe blocks and external libraries. With an elaborated instrumentation using both SFI and MPK, induces T-Rust a lower performance overhead than previous techniques. Thank you, and if you have any questions, ask me freely.